So now we are going to apply the idea of torque to a rotating system. And what we're going to see is that if we take Newton's second law for linear systems, which is F net equals ma, we can create a rotational analog. And what I mean by that is that these two situations are similar. Instead of writing F net, I'm going to write net torque. Instead of writing mass, I'm going to write moment of inertia. And instead of writing acceleration, I'm going to write angular acceleration. And so we can link torques to angular kinematics just the same way that we linked forces to linear kinematics. One thing to pay attention to, the unit for torque, you may remember, torque is force times the lever arm, and you want to take the perpendicular components of those, but the unit is the Newton meter. Be careful that it's not the same as work. Work is a linear situation and torque is a rotational situation. So the way that we tell the difference is we look at the situation. We look at the situation to determine if it's linear or rotational. Let's try an example. A potter's wheel of radius 0.5 meters and mass 100 kilograms is freely rotating at 50 revolutions per minute. Okay, let's remember what we learned about kinematics. So we have a radius, 0.5 meters. We have a mass, 100 kilograms. This is angular speed, 50 revolutions per minute. If I multiply by 2 pi radians per revolution and by 1 minute per 60 seconds, I would be able to convert this. Let's see, it'd be 100 pi over 60 or 5 pi over 3 radians per second. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim. Okay, so we've got a change in time, 6 seconds, and exerting a radial inward force of 70 newtons. What is the angular acceleration of the wheel? Now we have more information than we need to determine the angular acceleration of the wheel, but later on we're going to figure out the torque. So let's look at our kinematic information here. We've got time. We want acceleration. This is our initial angular velocity. And we know that it's going to stop. The wheel's going to stop. So the final angular speed is 0. And now we can use a kinematic equation to solve it. The one I'm going to choose is that final speed equals initial speed plus acceleration times time. So 0 equals, oops, not 50. I got to remember to use radians per second. 5 pi over 3 plus alpha times 6. I'd subtract 5 pi over 3 from both sides. Divide both sides by 6. And I get that alpha is equal to negative 5 pi over 18. Or if I put this as a decimal, let's see, 5 times pi divided by 18, I get negative 0.87 radians per second squared. Okay, next question. How much torque does the potter apply to the wheel? Okay, so in order to figure this out, I'm going to say that net torque is equal to moment of inertia times angular acceleration. The moment of inertia, this object is a disk. So if I go back to my pictures here, I'm going to use this moment of inertia. Solid cylinder, a disk is 1/2 mr squared. Okay, up above, I did determine the mass and the radius. So So I'm going to be able to put those in. And so let's do this. So I've got that the net torque is equal to the moment of inertia, which is 1/2 mr squared, and then times alpha, the angular speed. So the net torque is 1/2 times 100 times 0.5 squared times negative 0.87. And I would put that into my calculator. And I get 10.9, pardon me, negative 10.9. And the units on that are Newton meters. Okay, finally, find the coefficient of friction between the rag and the wheel. Okay, so I'm going to make a sketch here. So what's happening here is that the person is pushing inward like this. Okay, they're pushing inward. Oops. With 70 newtons of force. But the force that actually is stopping this thing is perpendicular to that. The force of friction, remember that friction acts perpendicular to a surface. So if I were to look at a top view of this, I didn't quite want all that. Get rid of these other bits. If I were to look at a top view, I'd have that F net going in toward the center, and then the frictional force would be perpendicular to the surface from my top view. The net force, because it's perpendicular, is also a normal force. Again, because this net force is perpendicular to the surface. We know that the force of friction is mu times the normal force. We know that the, we know that the normal force is 70 newtons. So what I need here is the frictional force. And the frictional force is what produces the torque. So the torque was 10.9 Newton meters. The force that I need is unknown, and the radius is 0.5. So when I divide this out, I get a force of 21.75 newtons. And now I'm ready to solve for mu. Mu is going to be equal to FF over Fn, which is going to be 21.75 divided by 70. Oops. Which is 0.31. And remember that the coefficient of friction has no unit. All right. Let's try a couple more examples. A bicycle tire radius 0.33 meters and mass 1.3 kilograms, 1.5 kilograms, is rotating at 98.7 radians per second. What torque is necessary to stop the tire in 2 seconds? Okay, so we know that torque is equal to moment of inertia times angular acceleration. A bicycle tire is basically a hoop, And the moment of inertia for a hoop is mr squared. Again, I could look that up above. So the moment of inertia is going to be 1.5 kilograms times 0.33 squared. So that is 0.163 kilogram meter squared. Okay, now if I had the angular acceleration, I've got the moment of inertia. If I had the angular acceleration, I'd be all set. So I can figure that out because I know that the initial speed of the tire is 98.7 radians per second. I know the final speed needs to be 0 if it's going to stop, and I know that the time is 2 seconds. So I'll look at my kinematic equations and find the one that I need. And I would get an angular acceleration of negative 49.35 radians per second squared. And now I'm set. I've got, I got the wrong thing here. I've got my moment of inertia, I've got my angular acceleration, and I can plug them both in. 0.163 times 49.35. And I would need a torque of 8.04 Newton meters. And this, we don't know which direction the wheel is going. This torque is going to oppose the motion of the wheel. Okay, next example. A 0.3 kilogram meter stick is held horizontally from one end. What is its angular acceleration when released? What is the linear acceleration of the end of the meter stick? This is one of my favorite problems, and we'll do an example of this in class. Come on, Notability, help me draw a meter stick. There we go. There's my meter stick. It's 1 meter long. We're going to have it have a pivot at one end. And what we're going to do is we're going to use the center of gravity here. The center of gravity of the meter stick is at a distance of 0.5 meters, halfway down, and the force of gravity is the weight of the meter stick, which is going to be 0.3 kilograms times 9.81. So that is 2.943 newtons of force. Okay, now this is going to create a torque. The torque is going to be the moment of inertia times the angular acceleration. And the torque is also the force times the distance. The force and the distance are perpendicular here, so I'm not going to worry about the rest of the formula. What I do need is I need the moment of inertia of a stick held at one end, and that is 1/3 ml squared. Oops. So now I'm going to make some substitution. So I'm going to start with the formula for torque. I'm going to substitute in the other formula for torque, force times distance from the pivot. I'm going to plug in the formula for moment of inertia, 1/3 ml squared, where L is the length of the meter stick, and what I'm looking for is alpha. Now, just a note, I could put numbers in here, but check it out. This force is actually Fg. It's actually the mass of the meter stick times G. And it turns out that that mass actually cancels out on both sides of the equation. Okay, so I've got G r equals 1/2 L squared alpha. I'll multiply both sides by 2. I get 2gr equals L squared alpha. And I get alpha equals 2gr over L squared. And that means alpha will equal 2 times 9.81 times the radius, which was 0.5. And the L is the length of the meter stick, that's 1. So the angular acceleration here is going to be 9.81, but that's radians per second squared. The question is, what is the acceleration of the end of the meter stick? Oh, I made a mistake here. Oh, why didn't you guys stop me? I knew something was wrong. This is supposed to be a 3, 1/3. My bad. Sorry about that. Did I make you nervous? There we go. Okay, that's more like it. Okay, so it's... There we go. 14.7. That's, I knew what the answer was supposed to be. I couldn't figure out why it wasn't coming out. Okay, so the angular acceleration is 14.7 radians per second squared. Now, if I want the actual acceleration of the end of the meter stick, that equals the angular acceleration times the radius. So that's 14.7 radians per second squared times the radius, which is 1 meter per radian. Oops. And when I multiply that out, I get that acceleration is 14.7 meters per second squared. So what actually happens is that the end of the meter stick falls faster than a falling object, because a falling object falls at 9.81. This falls at 14.7, which is kind of an unexpected result. Let's look at one more example together. In an experiment, an external torque is applied to the edge of a disc of radius 0.5 meters such that the edge of the disc speeds up as it continues to rotate. The tangential speed as a function of time is shown for the edge of the disc. The rotational inertia of the disc, okay, this is a fancy way of saying moment of inertia. So that's I, is 0.125 kilogram meters squared. Can the student use the graph and the known information to calculate the net torque on the edge of the disc? Okay, so here's the deal. This is tangential speed, which is basically velocity, and this is time. The slope of this graph is linear acceleration. We know that linear acceleration equals angular acceleration times r, the radius, which we do have. So we could get angular acceleration by dividing. And we do know that torque equals moment of inertia times angular acceleration, but check it out. We have both of those things. We have I. We could figure out angular acceleration, and so yes, we could figure out the torque. All right, thanks.